Have you ever stopped and wondered what it really takes to design a microchip? Well, today we're going to crack the code on that whole world. And we're not going to do it by reading a textbook. No, we're going to look at it through the lens of the incredibly high-stakes, brain-bending job interview every single VLSI engineer has to go through. I mean, just think about the smartphone in your pocket or the laptop you're probably watching this on. At their very core, you've got these chips with billions, literally billions, of tiny switches all firing in perfect harmony. How in the world do you even start to design something that complex? What kind of thinking does that actually take? You know, the journey to becoming a chip designer, it kicks off by proving you can handle some of the most difficult technical questions you can imagine. These interviews are legendary, and by breaking down the questions they ask, we can pretty much reverse engineer the entire process of how a microchip is born. So, where does a brand new chip begin? It's not with a piece of silicon. It starts as an idea, a blueprint. Before a single physical part even exists, the whole chip is designed and described completely in code, basically writing the language that the hardware itself will eventually speak. Okay, so a classic question for someone just starting out is to explain the difference between a latch and a flip-flop. These are the most basic memory cells on a chip, so what's the big deal? Well, a flip-flop only changes its mind, its state, on the exact tick of a clock signal. That precision makes everything predictable and stable. Latches, on the other hand, they're kind of open for business whenever the clock is high, which makes them way trickier to manage. Right, so building on that idea of timing, what happens when signals from totally different, unsynchronized parts of a chip collide? You risk this really dangerous state called metastability. It's like the circuit just freezes. It's stuck in this electronic limbo, caught between a 0 and a 1, and that indecision can crash the entire system. Preventing this is, without a doubt, one of the biggest challenges in digital design. It's pretty much a guaranteed interview question. So how do you do it? How do you build a system that's totally reliable when you've got signals just showing up at random times? And the answer just shows you how engineers think. The solution is actually surprisingly simple, but it's incredibly effective. What you do is you pass that unpredictable signal through two flip-flops, one right after the other. Now, the first one, it might go metastable, sure, but you give it one full clock cycle to sort itself out. By the time that signal hits the second flip-flop, the chance of it still being unstable is just astronomically low. Problem solved. And all of this stuff, the flip-flops, the logic, these synchronizers, it all gets written down in a special language, usually Verilog. But here's the thing. It's not like a normal programming language. You're not just writing steps for a computer to follow. You are literally describing physical gates and wires that are going to exist in a real piece of silicon someday. So once that blueprint is all written out in Verilog, what happens next? Well, this is where we jump from the abstract world of code into the physical one. We start this long, incredibly precise process of turning all that text into a real thing, a tiny microscopic city of circuits. And the most fundamental building block of our little microscopic city is the CMOS transistor. The easiest way to think of it is just as a perfect, tiny electronic light switch. And you have billions of these switches, all working together, forming the logic gates that do every single calculation on that chip. And this is where the interview questions start digging into some deep physics. An interviewer will show you a simple logic gate and ask this question. Now, it seems like such a tiny detail, but the answer tells them whether you actually get the physical reality of what you're trying to build. The answer is all about the physics of semiconductors. See, the particles that carry the charge in a PMOS transistor, they're called holes, are just slower. They're less mobile than the speedy electrons in an NMOS transistor. So to get the same amount of current flowing and make sure the gate switches on and off at balanced speeds, you literally have to make the PMOS transistor physically wider. It's a classic engineering trade-off for better performance. Now, arranging these billions of transistors is a whole process called physical design. And honestly, it's a lot like city planning, just on a nanometer scale. First, you do the floor planning, which is like zoning the different neighborhoods. Next, you lay down the power grid. Then comes placement, where every single building or cell is put in its exact spot. After that, you build the clock tree, the master timing signal, and finally, you do the routing, connecting everything with microscopic roads before the final sign-off. So once the city is built, a whole new problem pops up, making sure information can get from one side to the other fast enough. This whole phase is called static timing analysis, and it is a constant race against the clock, where every single picosecond matters. This is what directly determines how fast your apps load or how smooth your games run. And at the very heart of this race are two super important rules. First, a setup violation. That means your signal showed up too late for the next clock tick. It's like you missed your train. Then there's a hold violation. That means the signal changed too quickly, messing up the data from the last cycle. That's like the train leaving the station while you're still trying to get off. And here's the crucial difference. If you have a setup violation, the signal is too slow, you can often fix it by just running the whole chip at a slower speed. But a hold violation? That's different. Slowing down the clock doesn't help at all. The problem is fundamental to the logic path itself, which makes it a much more dangerous flaw in the design. This is where the real art of design comes in. To fix a too slow setup problem, you generally make the components bigger, more powerful. But to fix a too fast hold problem, you have to do the exact opposite. You actually add little delay buffers or even downsize the cells to intentionally slow the signal down. It's this incredibly delicate balancing act. But at the end of the day, it's not just about memorizing all these facts. The VLSI interview is really designed to test a specific way of thinking. It's about a mindset of logical, efficient, and sometimes really creative problem solving. All right, let's try one. This is a super common brain teaser. They'll ask, imagine you have two numbers, A and B. How do you swap their values without creating a third temporary variable to hold one of them? Just think about it for a second. And here's the answer. It's this beautiful, really elegant solution that uses the properties of the bitwise XOR operation. This is exactly the kind of clever, resource-efficient thinking that interviewers are looking for. It shows you really understand logic at its most fundamental level. So, what's the big takeaway for anyone who wants to do this for a living? Well, first, specialize. Pick a domain and get really good at it. Don't try to know everything. Second, always draw things out. If you're not drawing circuits or timing diagrams in an interview, you're not really explaining it right. And finally, know your own projects inside and out, because they will grill you on every single detail. From logic gates to timing analysis, these are the fundamental ideas that have built our entire modern digital world. The questions in these interviews, they're not just trivia, right? They are the keys to unlocking the ability to design the future. So the only question left is, what will you build with them?